Hello everyone, and welcome back. Today we're going to continue our exploration of single variable calculus by just going over a few examples of derivatives just for practice or review. So let's start off with this function, y is equal to the cube root of 5x squared plus sine x plus the arctangent of x, which some people will also write as tan with a -1 superscript, then x. So the first thing that we have to observe is, okay, what type of function do we have to deal with here? So obviously we have a cube root function controlling all of this other thing underneath that radical sign. So this is obviously a chain rule problem. So what I like to do before I start differentiating is write that as a fractional exponent just in case you're not comfortable with that. So we can equivalently write this as 5x squared plus sine of x plus the arctangent of x all raised to the power of 1 over 3. So we can use the power rule since that is the function that controls that interior, and we're going to get what? So we're going to have the derivative of y with respect to x is going to be equal to, so we're going to bring that power down, and then we're going to subtract that power by 1 while keeping the interior function fixed, right? So 1/3 minus 1 is going to give us minus 2/3. And then we're going to multiply by the derivative of the interior function, and make sure to put parentheses here just in case you forget. So the derivative of 5x squared by the power rule is going to be 10x. The derivative of sine we know is going to be equal to the cosine, and the derivative of the arctangent function is going to be 1 over 1 plus x squared, and that is the derivative of that original problem. So quite simple. So let's look at a second example. Let's assume we have the very famous univariate normal distribution 1 over sigma, the square root of 2 pi, times e to the minus 1/2 x minus mu over sigma, the quantity squared. Here, let us assume that mu is a real number and sigma is a positive real number, i.e. they're just constants. So if you're not comfortable working with a lot of constants in your expression, you can always cluster constants together. For example, 1 over sigma squared of 2 pi is just a constant. So for example, we can just call that c for the time being, and we can equivalently write this as y is equal to a constant times e to the minus 1/2 x minus mu over sigma, the quantity squared. The reason I'm not touching that interior term with the mu and sigma is because we have the variable x there, so we don't want to mistakenly represent that as a constant when it's not. So what we have here is a chain rule. So we're going to have that the derivative of y with respect to x is going to be equal to, so we can factor that constant out of the derivative operator, and the derivative of an exponential is itself, so we're going to have e to the minus 1/2 x minus mu over sigma to the power of 2, but if it's a exponential with another base besides e, you would multiply by the natural log of that base, but the natural log of e is 1, so we don't need to write that. Now we need to multiply by the derivative of the interior function that exponentiation is controlling here, and that's the minus 1/2 something squared. So minus 1/2 times 2 is just going to be minus 1. So we're going to have minus 1 times x minus mu over sigma, the quantity 2 minus 1, which is 1, but I'm not going to write that, but that's going to go to 2 minus 1 once we bring that 2 down, so we're just doing a power rule. And now we're going to multiply by the derivative of that interior function. So what's the derivative of x minus mu over sigma? So keep in mind, we can always decompose fractions if we have a singular term on the bottom. So we can write that as x divided by sigma minus mu divided by sigma. Mu over sigma is just a constant, so that's just going to differentiate to 0. And then we have x over sigma, which can also be rewritten as 1 over sigma times x, which is just a linear function whose slope is 1 over sigma. So the derivative of x minus mu over sigma, which is just a linear function, is just that term 1 over sigma, so I can just write that over here. So we're going to just have 1 over sigma, the constant there. Now that I have that, that's practically my derivative, but you probably want to make this term a little bit more nicer to look at. And I'm also going to bring back my c that I originally had. So keep in mind that c was equal to 1 over sigma, the square root of 2 pi, and we're going to have a sigma times that sigma there, so we actually have 3 sigmas going on here. So we're going to have dy over dx is going to be equal to minus 1 over sigma cubed times the square root of 2 pi, and then we're going to have this x minus mu term, there. And then we're going to have this e to the minus 1/2 x minus mu over sigma, the quantity squared. If that makes you uncomfortable that x minus mu just by itself, we can always just bring that sigma back in and write it as x minus mu over sigma, the quantity, multiplication, and then reduce that power from 3 into 2. And that gives you something a little bit more easier to look at and interpret, especially if you have some probability and statistics background, but that would be the derivative of the original function that we had. The next few examples that I want to work through are cases where y is not by itself, i.e. y is not isolated. In general, you can find the slope of curves that aren't even functions. For example, if we have a graph of a shape that looks like this, there are tangent lines to this curve at a various number of points, and in particular, one value x in the domain of a relation might have several slopes associated to that, and that is perfectly normal. So we still should be able to find, for example, dy over dx for a particular given relation, and that's what we're going to do here. So let's assume that we're interested in finding dy divided by dx, i.e. we want the derivative with respect to x of the variable y. So since we're going to be applying a d over dx operator to both the left and the right, that's going to be how I'm going to start this problem. So I'm going to start off by doing the derivative with respect to x of the left-hand side, and then that's going to be equal to the derivative with respect to x of the right-hand side. Right, so we're doing implicit differentiation here. So once I have that, then I'm just going to distribute that over sums and differences because we know derivatives are linear operators. So the derivative with respect to x of x squared is going to be 2x, and the derivative with respect to x of y squared is going to be 2y times the derivative of y with respect to x, and that dy over dx there is a result of the chain rule. So then we're going to have the derivative of x, which is just going to be 1 with respect to x at least. And then we're going to be doing a product rule for that because of something times something else. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. So that's that product rule term there. And then the derivative of y is just going to be dy divided by dx. Right? So that is our result. So our goal is to find dy over dx, and here we have 1, 2, 3 instances of that, so I just need to shuffle them to the same side and shift everything else to the other side. In particular, 2x, 1, and y needs to be on the right, and everything underlined in pink is going to be on the left. So once I isolate everything, we're going to have 2y times dy over dx minus x times dy over dx minus dy over dx, let's multiply it by 1 just for fun, and that's going to be equal to 1 plus y minus 2x. Once I have my dy dx's all to the same side, I can factor out that out of all of those terms and divide by everything else that remains. So on the right hand side, we're going to have 1 plus y minus 2x over 2y minus x minus 1, and that would give you the result for dy over dx. Keep in mind, some people will multiply top and bottom by -1, and you can write that as 2x minus 1 minus y over x plus 1 minus 2y to also get an equivalent expression, because some people prefer it written one way versus another, but nonetheless, they are the same exact answer. All right, so let's just do a couple more of these implicit differentiation problems. Let's say x over y minus y over x is equal to x plus y. Let's practice some chain rule applications. So we're going to have a quotient there, and a simple derivative on the right-hand side. So just like the last problem, I'm going to take the derivative of the left-hand side, and then the derivative of the right-hand side, with respect to x on both sides, of course. So for the top, keep in mind it's bottom derivative top minus top derivative bottom over bottom squared for the quotient rule. So we're going to have bottom times the derivative of the top minus the top, and I'm focusing on this one, minus the top times the derivative of the bottom, which I'm just going to write y prime, so I'm going to let y prime denote dy over dx just to keep notation short, all over the bottom squared. And then I'm going to do the same for this one. So minus, so bottom derivative of top minus top derivative of bottom over bottom squared. And that's going to be equal to 1 plus y prime on the right-hand side. So once I have that, what I want to do is get a common denominator. So I'm going to multiply top and bottom of this one by x squared and top and bottom of this one by y squared. So then I can get them on the same side. And then I'm going to get, what do I have? So y x squared minus x cubed y prime minus xy squared y prime plus y cubed over x squared y squared equals 1 plus y prime. Right? And if you're not sure where that plus sign comes from, it comes from that distribution of that minus sign. All right, so we get that particular expression. Let's move my x squared y squared to the right-hand side by multiplication. And everything that does not have a y prime, for example, x squared y and y cubed, I'm going to shift over to the right-hand side as well. So once I have that, then I'm going to have minus x cubed y prime minus xy squared y prime is equal to, let's see, x squared y squared plus x squared y prime. That's what you get when you distribute that into that bracket. And then we're going to have minus x squared y minus y cubed when we isolate those terms that don't have y prime into the right-hand side. We still have this lonely little y prime there, which means we need to shift that to the left-hand side. That's why I actually had to distribute that x squared y squared into that red bracket, else we can't isolate that further. So once I have that, I'm going to have dy dx is going to be equal to, so we're going to have x squared y squared minus x squared y minus y cubed on the right-hand side all over minus x cubed minus xy squared minus x squared y squared on bottom, right? Notice that we do have a couple of x's that are in common. In particular, we have one x on top, and we don't have a y in this lonely little term, which is actually quite sad. So I'm just going to write this as x times xy squared minus xy minus y cubed all over, let's write it as minus x squared with an x factored out minus y squared minus xy squared on the bottom. And then those x's are going to cancel out. So I'm just cleaning up this derivative expression, which is most of the time optional, depending on who you're talking to. And that's going to give me what? I personally don't like 3 negatives on the bottom, and I do have one positive coefficient up top, and I have 2 negatives on top as well. So I'm just going to multiply top and bottom by -1, and that's going to give me y cubed plus xy minus xy squared, all divided by x squared plus y squared plus xy squared, and that I think is a very nice looking derivative expression for my original curve. All right, so that's pretty nice. Let's do one other. Let's do 10 is equal to x to the y. A very gentle looking relation, I think. So every time you have a variable to a variable, I always recommend doing logarithmic differentiation. That is starting by taking the natural logarithm of both sides of this expression. So we're going to have that. And then we can bring that exponent down in front of that natural log, and then we're going to have a nicer expression to deal with. So we're going to have the natural log of 10 is equal to y times the natural log of x. Keep in mind, natural log of 10 is just a constant, so when we take the derivative of both sides, in particular the derivative with respect to x of y times the natural log of x, and then the derivative with respect to x of the natural log of 10, the natural log of 10 is just going to go to 0, so it doesn't really matter what that is. So over here we have a product rule, so first derivative second plus second derivative first. So we're going to have first derivative of natural log is 1 over x, so first derivative second plus second, and then let's do dy over dx, derivative first, and that's going to be equal to the derivative constant is equal to 0. So I'm going to just move that to the right hand side and then divide by the natural log of x. So that's going to give us dy over dx is equal to minus y over x all divided by the natural log of x, which we can actually write in a nicer way as dy over dx is equal to minus y over x natural log of x. And that would be your resulting derivative. All right, let's get into an example with a trigonometric function, in particular an inverse trig function, because sometimes it's easy to forget these relations. And also let's make it hyperbolic. So let's do an inverse hyperbolic cotangent of x. Let's just keep it very simple. So when you're working with hyperbolic tangents or even regular trig functions inverses, it's always important to keep in mind sine squared theta plus cosine squared theta is equal to 1, and also hyperbolic cosine squared theta minus hyperbolic sine squared theta is equal to 1. Those are the important Pythagorean identities for circular and hyperbolic trigonometric functions, which often come useful when you're trying to derive, prove, or even recall derivatives of inverse trigonometric functions. Okay, so what do we have here? So the first thing I'm going to do is get rid of this inverse term, right? Because keep in mind, if I take the hyperbolic cotangent of inverse hyperbolic cotangent of x, I'm just going to get x on the out-hand side. So what I have there is I'm going to have the hyperbolic cotangent of y is just going to be equal to x, right? And then still my goal is to find what is dy over dx equal to. As long as you know the derivative of hyperbolic cotangent, then we're safe. Now, let's assume that you don't remember what the derivative of hyperbolic cotangent is. So let's just do a brief excursion and see what that would be. So the derivative of hyperbolic cotangent, let's do it of y, since that's what we have on the left hand. Actually, no, let's not do that. Let's keep it x on both. So what is the derivative of just hyperbolic cotangent of x? So that's just going to be equal to the derivative of hyperbolic cosine, derivative of hyperbolic sine. Right, so bottom, derivative of top, derivative of cosh is sinh. There's no minus in the hyperbolic world. Minus, so bottom derivative of top minus top, derivative of hyperbolic sine is hyperbolic cosine, all over the bottom, squared. So we have hyperbolic sine squared, so hyperbolic sine squared x minus hyperbolic cosine squared x, all divided by hyperbolic sine squared x. Notice that the numerator is sine h squared minus cosine h squared, which is the reversal of cosh squared minus sinh squared. Therefore, the top of this expression is going to be equal to minus 1. So we're going to have minus 1 divided by hyperbolic sine squared of x, which is just going to be equal to minus hyperbolic cosecant squared x. So if you remember, the derivative of circular cotangent is negative cosecant squared, and the derivative of hyperbolic cotangent has a parallel analogous relationship with its hyperbolic counterpart. All right, so now we've recalled how to find the derivative of just normal hyperbolic trig functions. Now let's get back to our main story. So we have the hyperbolic cotangent of y is equal to x, and I'm going to take the derivative of both sides with respect to x because I want to find dy over dx. Right? So what is that going to give me? So we know that the derivative of hyperbolic cotangent of something is going to be equal to minus hyperbolic cosine squared of something times the derivative of that something with respect to x, and the derivative of x with respect to x is just equal to 1. Right? So from here, what do we have? So we have dy over dx is equal to minus 1 over hyperbolic cosecant squared of y. Right? So that is our expression. But keep in mind that we have dy over dx is equal to a function of y, and that's not good. And do keep in mind that y is equal to arc hyperbolic cotangent of x. Right? So how are we going to write this as a function of x? Well, we would have to use our trigonometric identities in order to manipulate this. So let's just take a quick detour and see where to go from here. So we know that hyperbolic cosine squared of y minus hyperbolic sine squared of y is equal to 1. And what do I have here? Well, hyperbolic cosecant squared of y is equal to what? Well, I don't know. So what I want to do is I want to divide something by, let's see here, how can I get a hyperbolic cosecant squared? Well, what I can do is write that as dy over dx is equal to minus hyperbolic sine squared of y. And then I can play with this identity instead, right? But still, I want to write that as a function of x. So minus sine squared y is going to be equal to, well, I can just solve this equation for that, and I can multiply both sides by, or subtract both sides by, 1 minus cosine squared of y, and that's going to give me dy over dx is equal to, so minus sine hy is going to be equal to 1 minus cos squared of y, right? But still, we haven't really got anywhere because we still have a function of y, right? But there is some trickery that you can do here, or possibly even before this step. Because if you get playing with these trigonometric identities, there are infinitely many ways that you can manipulate these. And we're like, okay, well, we can solve for sinh squared y here. We don't really get anywhere. So maybe that's not the step that we need to take. So what we can do, instead of subtracting and just reciprocating that, what we can do is we can do the same thing we did when we were deriving our other two Pythagorean identities for circular trig functions. For example, we can divide both sides of this expression by hyperbolic sine squared, or we can divide both sides of this expression by hyperbolic cosine squared. And I'm going to divide by both sides by hyperbolic sine squared of y. And you'll see why I choose this one in just a moment. Because hyperbolic cosine squared of y divided by hyperbolic sine squared of y is hyperbolic cotangent squared of y. And we do have a relationship for that, which we'll recollect in a moment. And over here we have 1 over sinh squared y, which is going to be equal to 1 over hyperbolic cosecant squared of y. And we know what that exactly is, right? Not 1 over, but hyperbolic cosecant squared of y. Okay, so we have this particular expression. So now we can just replace hyperbolic cosecant squared of y with cotangent hyperbolic squared y minus 1. So that's going to give us what? So we're going to have dy over dx is equal to minus 1 over hyperbolic cotangent squared of y minus 1. And you're like, well, that doesn't really help, but we can get rid of this minus sign briefly. We can make that as 1 over 1 minus hyperbolic cotangent squared of y. And you're like, but you haven't really changed anything. It's still a function of y. But keep in mind, y is equal to inverse hyperbolic cotangent of y. And if we substitute that into that expression, the hyperbolic cotangent and the inverse hyperbolic cotangent cancel, right? And that's exactly what we want. And that should be y, not x, of course, right? So once we substitute that into this expression, then we have that the derivative, let's just go back to the original problem, the derivative of inverse hyperbolic cotangent of x is just going to be equal to 1 over 1 minus x squared. Very, very nice, isn't it? And that's the derivative of that function, how you derive all the pieces that precede it. Let's do another example of implicit differentiation with a couple chain rules on both sides of this expression. So on the left we have arctangent of something, and on the right hand side we have something squared. So as usual we're going to be differentiating with respect to x of the left hand side, and we're going to be differentiating with respect to x on the right hand side. So the derivative of arctangent of something is 1 over 1 plus something squared. So the left-hand side is going to turn into 1 over 1 plus something squared, and then we're going to multiply by the derivative of that something. So the derivative of x is going to be 1, and the derivative of y is going to be dy over dx, which I'm again going to abbreviate dy over dx as just y prime. And then on the right-hand side, we're going to have something squared, so that's going to be 2 times something to the power of 1, and then times the derivative of that interior function. So we're going to have the derivative of x squared, which is 2x, and then first derivative second plus second derivative first. That's going to be the product rule, and then plus the derivative of y squared, which is going to be 2y, y prime. Right? So once we have that, now we need to isolate our y prime terms. Now notice that we have a lot of foiling going on. You only need to FOIL things that have y prime in them. Notice that this expression does not have y prime. This expression doesn't have y prime either. So what I'm going to do is I'm going to create new functions to make my algebraic representation a lot easier. So I'm going to call this function here, I'm going to call this a of x, and I'm going to call this expression here, and I'm going to call that b of x. And keep track of what you define these functions to be. So what I have here is I have a of x times 1 plus y prime is equal to b of x times 2x plus xy prime plus y plus 2y y prime. Right? And that's a lot easier to look at. Now I'm going to distribute. So I'm going to distribute my a into the first and second term, and I'm going to distribute my b into these four terms. So once I have that, I'm going to have a of x plus a of x times y prime, and you can just call it a or b just to make notation simpler, but keep in mind they are functions of x, not constants. And that's going to be equal to, let's just do that just to make life easier for us. Let's just call it a and a. Keep in mind they're not constants, they're functions of x. And that's going to be equal to, let's call it 2bx plus bxy prime plus by plus 2byy prime. So now we need our y primes on the same side and everything else to the other side. Right? So once I have that, I'm going to have dy over dx is going to be equal to, so everything in green is going to be on top, so 2bx plus by minus a, and everything on the bottom is going to be from the left. So we're going to have a minus bx minus 2by, and that would be your answer, where these functions, where a is equal to 1 over 1 plus x plus y squared, and b is equal to 2 times x squared plus xy plus y squared. And that would probably be a preferred way of writing that particular expression. So we're using substitution to make our life a lot easier here. Let's do another example where we're actually going to use a lot of substitution because our functions are going to be very, very messy here. So we're going to have x to the 2y plus 2xy plus y to the 2x is equal to x squared plus 2xy all over x plus y is equal to y squared plus y squared, not is equal to. Right? So the first two functions that we need to deal with here are x to the 2y and y to the 2x, which are both pseudo-tetration functions. The rest of them, a product rule, a power rule, and a quotient rule, aren't really that difficult to deal with. So we need to tackle how to take the derivative with respect to x of these two pseudo-tetrational functions before we proceed into the actual solution of this expression. So let's say, I don't know, let's say w is equal to x to the 2y. And what we want is the derivative of w with respect to x. Now before I get into that, I'm going to take the natural log of w, and I'm going to have the natural log of w is equal to 2y times the natural log of x. So I've just used the power rule for logarithms there. And then I'm going to take the derivative with respect to x of both sides. So the derivative with respect to x of 2y times the natural log of x, and then I'm going to have 1 over w times w prime is equal to, so then I'm going to have first derivative of the second plus the second times the derivative of the first. There, I factored out my 2 so I didn't have too many constants. And then what I'm going to have is w prime. So w prime, which is just a fancy way of saying the derivative of w with respect to x, which is what I want. Right, so the derivative of w with respect to x is just going to be equal to w, which is x to the 2y, and that's going to be a 2 there. And then we're going to have y over x plus the natural log of x times y prime. Right, so that's going to give us the first expression. So let's just box that off. And we also have to do it for the other expression as well. Let's call the other expression z. So z was equal to y to the 2x, right? So when I say z prime, that's just going to be equal to dz dx, which is also something that we need. So what I'm going to do is I'm going to take the natural log of z, so I'm going to have 2x times the natural log of y, and then take the derivative of both sides with respect to x. So I'm going to have 1 over z times z prime is equal to first times the derivative of the second, plus the second times the derivative of the first, which is just going to be equal to 1. Which, keep in mind, is very different from the other one because the other one had y prime. This one is just 1, right? So don't be quick to try and mix them if you're not comfortable with that. And that gives us that. So that's pretty nice. So the derivative of z with respect to x is going to be equal to, and that's a 2, and that's a z with the line through it. So we're going to have 2y to the 2x times x divided by y plus the natural log of y. Okay, so that's actually pretty nice, actually. That's actually very, very nice, right? Oh, we're missing something. Where's my y prime? I'm like, oh, that's actually too friendly looking because there's no y prime there. Okay, now we're looking pretty good. All right, so that's the derivative of z with respect to x and the derivative of w with respect to x. Now we're going to be distributing these things here. So let's just get that over with. So let's distribute that. So the derivative of w with respect to x is going to be equal to 2yx to the 2y, let's say minus 1. And then we're going to have plus 2x to the 2y natural log of x times y prime. It's the first important equation. And then the second important equation is going to be dz dx is going to be equal to, let's write it as 2xy to the 2x minus 1 times y prime plus 2y to x natural log of y. Okay, so those are the two ugly expressions that we need to deal with. The rest is going to be straightforward. All right, so let's bring back what our original problem was. So x to the 2y plus 2xy plus y to the 2x is equal to x squared plus 2xy over x plus y squared. Okay, so take the derivative with respect to x of both sides. So we get the derivative of that with respect to x, which is just dw over dx, plus 2 first derivative second plus second derivative first. And then over here we had the derivative of z with respect to x. And that's going to be equal to 2x plus, now we have a quotient rule, that's exciting. So bottom derivative of the top, so we're going to have 2 first derivative second plus second derivative first, so bottom derivative top plus top minus top derivative bottom, so first is the derivative of x, which is 1, plus the derivative of y, which is y prime, so bottom derivative top minus top derivative bottom all over bottom squared plus 2y y prime. This is exciting, isn't it? All right, so let us substitute our ugly dz and dw expressions into this, and let's call things as quickly as possible. So we're going to have 2y x to the 2y minus 1 plus 2x to the 2y ln of x y prime. And then we're going to, let's just distribute that. So we're going to have 2xy prime plus 2y. So that's going to be that term. And then plus 2xy 2x minus 1 times y prime plus 2y 2x natural log of y is equal to the right-hand side, which is going to be 2x plus, let's decompose this by dividing. And let's do 2, let's be careful here. Let's do 2xy prime plus y over x plus y, because x plus y is in common with there and there. And then over here we have minus 2xy minus 2xy y prime all over x plus y, the quantity squared, plus 2y y prime. All right, now we need to make sure we cluster things together as we need. So this does not have y prime in it. This does not have y prime in it. This does not have y prime in it. So let's give that a name. So a is going to be equal to 2yx, 2y minus 1, plus 2y, plus 2y, 2x, natural log of y. So that is the first thing I don't want to deal with anymore. It doesn't have any y primes in it. So once I simplify that, then my left-hand side actually simplifies a lot, because we're just going to have a plus, and then we're going to have y prime factored out of 2x to the 2y natural log of x plus, what else do we have here? 2x, and then we have plus 2xy to the 2x minus 1 on the left-hand side. All right, now let's play with this right-hand side a little bit. So we have, that doesn't have a y prime in it. This doesn't have a y prime in it, and this doesn't have a y prime in it either. So I'm going to define b to be equal to 2x plus y over x plus y minus 2xy over x plus y, the quantity squared. That's the second thing I don't want to deal with. And that's going to be equal to b plus 2xy prime all over x plus y plus 2xy prime all over x plus y, the quantity squared, plus 2y y prime. So our answer is becoming a little bit more nicer to deal with, isn't it? Okay, so the next thing I don't want to deal with is this thing, so I'm just going to call that c. So c is going to be equal to 2x to the 2y, natural log of x, plus 2x plus 2xy to the 2x minus 1. So that's going to make that a lot simpler. And on the right-hand side, we're going to factor out a y prime, because we can write that as y prime times 2x over x plus y plus 2xy over x plus y, the quantity squared, plus 2y, and I'm going to call that thing d. So we're going to have d is equal to 2x over x plus y plus 2xy over x plus y, the quantity squared, plus 2y, because I don't want to deal with that anymore. So using all of our substitutions up to this point, what do we have? So we're going to have a plus y times c is equal to b plus d y prime. Isn't that so beautiful to look at? That's so nice. All right, so I'm just going to move my y prime terms to the left-hand side and everything that doesn't have y prime to the right-hand side. So I'm going to have dy over dx is going to be equal to b minus a all over, no it's not, y prime on the left. So we're going to have c minus d all over b minus a, where a, b, c, and d were defined above. And that's probably the most practical and sensible way to approach derivative problems, where you just have nasty, ugly looking functions of x and y that don't really have any significance in terms of the actual y prime term, right? i.e. substitution is your best friend in these types of cases. The last two examples that I want to talk about today in terms of derivative practice are examples that come up later on in single variable calculus, but I just want to mention them here just in case you are familiar with integrals or infinite series, or maybe you just want to sort of get a look ahead at some of the fun, exciting things that we plan to discuss. So let's assume we have a function y of the variable x, and it's defined to be equal to this infinite series, the sum from k is equal to 0 to infinity, negative 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial, where that negative 1 to the k is what we usually call a alternating term. And you may even recognize this infinite series as the Taylor series for the function sine. So we know the derivative of sine is equal to cosine, so if we differentiate this function, we should also get the Taylor series for cosine as well. But if you don't know anything about Taylor series, you can just look at this as an infinite series and be like, okay, what's the derivative of an infinite series equal to? So what I can do is, in case you're not familiar or comfortable with this notation, is you can actually expand this out into its term-by-term expansion. So if we replace k is equal to 0, k is equal to 1, k is equal to 2 for the first few terms, what you're going to have here is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus x to the 9 over 9 factorial minus plus and so on. So you're just going to have an alternating sum of odd powers of x, because keep in mind that's over 1 factorial, over the odd numbers factorial. Right? So what we're going to do is we're going to take the derivative with respect to x of this expression. Right? So the derivative of x is just going to be equal to 1. That's not exciting. The derivative of x cubed is going to be equal to 3x squared over 3 factorial. And then we're going to have 5x to the 4 over 5 factorial minus 7x to the 6 over 7 factorial plus 9x to the 8th over 8 factorial minus plus and so on. Now, if you don't remember what factorials are, if we just look at, for example, 7 factorial, that's the same as 7 times 6 times 5 times 4 times 3 times 2 times 1. And if we look at this particular term, notice that we have a 7 on top. So if you have a 7 on top, notice that those 7's cancel, and we're just left with 1 over 6 factorial on the bottom. So we can write this as dy over dx is equal to 1 over, and some people write this as 0 factorial, which is also equal to 1. And we can write 1 also as x to the power of 0. This is going to help us write this in series notation in just a moment. So 3 cancels with the 3, so we're just going to be left with 2 factorial, and then plus x to the 4 over 4 factorial, minus x to the 6 over 6 factorial, plus x to the 8 over 8 factorial, minus plus, and so on. So that is our derivative in expanded form. Now let's just write this in series form. So we just have an alternating sequence of even terms. So the sum from k is equal to 0 to infinity. Negative 1 to the k is going to take care of that alternating term. X to the 2k, that's going to give us our even powers of x. All over 2k factorial, that's going to give us our even factorials on the bottom. And that's going to give us the derivative of that original Taylor series is what we call. Now, let's look at our last example, which is in terms of integrals, which are sometimes referred to as anti-derivatives, which are used for finding areas in curves, under curves, and several other things. So let's do the integral from x squared to sine x of the function cosine of t divided by t dt. All right, so what is the integral of a function? So the indefinite integral of a function is a function family whose derivative is equal to this particular thing here. So since you don't know the derivative of a function that gives you cosine t over t, let's just give it a name. Let's just give it the name capital C of x, and let's assume that the derivative of c of x is equal to cosine of x over x. Let's just give it that name, right? So if that is the case, that means y can be represented as the integral. Well, the integral of cosine t over t is just going to be equal to c of x, c of t, and then we need to evaluate this as t goes to sine of x, and as t goes to x squared, which means this is going to be equal to c composed with sine x minus c of x squared. And that's what we refer to as the fundamental theorem of calculus, this step here. Okay, now we have an alternative representation of y. So y is just going to be equal to c sine of x minus c of x squared. Now I'm just going to take the derivative with respect to x of both sides. And keep in mind the derivative of c of x is equal to cosine of x over x. This is our definition. So the derivative of y with respect to x, so we're just going to use the chain rule twice. So the derivative of c of something is equal to cosine of something over something times the derivative of something, which is cosine. And then the derivative of c of something is going to be equal to, again, cosine of something over something times the derivative of that something, which is 2x. So once we have this, then we just need to clean up this expression. So we're going to have dy over dx is equal to, so cosine divided by sine is going to be cotangent. So we're going to write that as cotangent times cosine of sine. And then minus, we have a 2 hanging out there, and then we have a cosine of x squared, all divided by x there, and that's probably a nice way of writing that expression for the derivative. So I hope you enjoyed this little quick overview of 10 basic functions just to review your derivative skills. Hope you enjoyed, and I'll see you in the next video. Take care.